Hi, this is Dr. Bay and Bugsy, and today we're going to learn about part one of constitutional isomers versus conformations. We'll delve into how to draw Newman projections for linear alkanes, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly reply, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Isomers are molecules with the same molecular formula, but they have different arrangements of their atoms in space. Two types of isomers are constitutional isomers and conformational isomers. Constitutional isomers have the same molecular formula, but they have a different connectivity of atoms. In order to be constitutional isomers, at least one bond had to have break and reconnect at a different atom. Take this example of C4H10. In the top example, we have butane, where all four carbon atoms are drawn in a zigzag format. But if we break off the last carbon on the right with its three hydrogens and reattach it, we can redraw this molecule as 2-methylpropane. If we count the number of carbons and hydrogens in each of these two molecules, they both contain 4 carbons and 10 hydrogens, but only differ in connectivity, which means that these two compounds are indeed constitutional isomers. But today we're going to focus on conformational isomers, which allow us to analyze a specific bond and how each substituent interacts with one another through what's called a Newman projection. A conformation is a rotation about a carbon-carbon single bond of a compound. A Newman projection is a type of drawing that represents a molecule after 90 degrees of rotation. So, how do you draw a Newman projection if you're given a molecule like butane? First, you're going to number the carbons in your molecule and then determine which two carbon atoms you would like to study. So let's specifically study the C2-C3 bond. You can even add an eye with an arrow pointing towards that specific bond. The second step is that you're going to draw the first carbon of the bond you're studying as a dot, which in our example would be the C2 carbon in blue. Then draw the second carbon of the bond, which would be C3, as a circle, which is shown in green. Then draw the atoms that are bonded to C2, where each atom is about 120 degrees apart from one another. The hydrogen atom that is on a wedged bond will point to the right, the hydrogen atom on a dashed bond will point to the left, and the methyl group that is in plane will point up. Next, draw the atoms bonded to C3, which would be around the circle. You're going to draw each of these green substituents about 60 degrees apart from the blue substituents. The hydrogen on a wedged bond will point to the right, the hydrogen on a dashed bond will point to the left, and the methyl group that's in plane will point downwards. Then we can rotate the substituents around the C3 position to get different conformations. But let's get into more detail on what that rotation means. Now, this is the Newman projection of butane that we just drew. Notice how the blue methyl group is pointing up while the green methyl group is pointing down. When your two largest groups are pointing in opposite directions, this is called an anti-conformation because they have a dihedral angle of 180 degrees. Now, if we rotate the substituents around C3 by 120 degrees, we get the next conformer. So notice how both methyl groups are now adjacent to one another. This is called a gauche conformation, where the two largest groups have a dihedral angle of 60 degrees. And since the methyl group is pointing to the left, that means the methyl group is on a dashed bond, as shown in the molecule below. Now, if we rotate the molecule again by 120 degrees, still keeping the blue C2 substituents in the same spots and only moving the green substituents, then we get the next conformer. The green methyl group moved to the right side, which means it's now on a wedged bond, as shown in the molecule below. And since the two largest substituents are still adjacent to one another, they are still in a gauche conformation. And all three of these conformations are considered to be staggered because there's a relatively equal amount of space between all six substituents shown in the Newman projection. But if you pretend that the green circle is like a clock, the green methyl group is the clock pointer and it's currently pointing at the 6 o'clock position. The pointer cannot go straight from 6 o'clock to 10 o'clock in the first gauche conformation without moving through 8 o'clock. That said, there is an additional conformer in between going from the anti-conformation to the gauche conformation. If we rotate C3 by only 60 degrees, we get what's called an eclipsed conformation where substituents at the C2 position align directly with the substituents at the C3 position. If we rotate C3 by 60 degrees again, then we get the staggered gauche conformation. And you can imagine that the staggered and eclipsed conformations alternate as the substituents around C3 rotate. So how do all of these conformers rank within one another based on stability? The staggered anti-conformation is the most stable, followed by the staggered gauche conformation, and then both eclipsed conformations are the least stable. But what determines this stability and why? What differentiates each conformer from one another is strain, which is the repulsion between electrons of different atoms within a molecule. There are two types of strain that are involved in conformational analysis seen in Newman projections, and that would be torsional strain and steric interaction. Torsional strain is the repulsion that arises between atoms or a group of atoms when a molecule is rotating around a sigma bond. So this is mainly seen in eclipsed conformations. Torsional strain can be alleviated by rotating a molecule around a sigma bond to reach a more stable staggered conformation. And this strain occurs when bond electrons pass by each other as a molecule is rotating. And secondly, steric interaction is the repulsion between two atoms or a group of atoms when they are way too close to one another, which is mainly seen in staggered gauche conformations. And steric interactions cannot be alleviated by rotating the molecule around a sigma bond, and it occurs when the distance between bulky groups of a molecule is just too close. So each type of strain costs a certain amount of energy. The less stable a conformation is, the higher amount of strain energy it takes to form that conformation. And each type of strain can be broken down into their energy costs. So when two hydrogen atoms eclipse with one another, this is a type of torsional strain that costs 4 kilojoules per mole. When a methyl group and a hydrogen atom eclipse, this is also torsional strain, but costs a little more of 6 kilojoules per mole. When two methyl groups eclipse, this is a combination of both torsional strain and steric interaction, which pays a hefty energy cost of 11 kilojoules per mole. And lastly, when two methyl groups are gauche to one another in a staggered conformation, this is a type of steric interaction that costs 3.8 kilojoules per mole. So with those energy values in mind, we can decompose how much energy it'll take to form each of these conformations. So the staggered anti-conformation again is the most stable and costs 0 kilojoules per mole since there are no unfavorable strain interactions involved. Next, the staggered gauche conformation has one methyl-methyl gauche interaction which costs 3.8 kilojoules per mole. The next eclipsed molecule contains two methyl hydrogen eclipsed interactions, which cost 12 kilojoules per mole, as well as one hydrogen-hydrogen eclipsed interaction that costs 4 kilojoules per mole. So if we add up these two values, this conformation costs in total 16 kilojoules per mole. And the least stable eclipsed conformation contains one methyl-methyl eclipsed interaction that costs 11 kilojoules per mole, as well as two hydrogen-hydrogen eclipsed interactions that cost 8 kilojoules per mole. So in total, this eclipsed conformation pays a hefty energy cost of 19 kilojoules per mole. So you can see, just based off of the energy values, the most stable anti-conformation costs nothing, while the least stable eclipsed conformation costs the most. And we can plot these values on an energy diagram where the x-axis is the dihedral angle about the C2-C3 bond that we wanted to investigate, and the y-axis shows potential energy in kilojoules per mole. And you can see how the green methyl groups interact with one another throughout each step of the rotation. Starting on the bottom left, we have our most stable staggered anti-conformation. As we rotate by 60 degrees at a time, we reach the eclipsed conformation at 16 kilojoules per mole. Then the energy goes down to the staggered gauche conformation at 3.8, then back up to 19 kilojoules per mole to get to the next eclipsed conformer, then back down to the staggered gauche conformation at 3.8 kilojoules per mole, back up to the next eclipsed molecule at 16, and then all the way back down to the staggered anti-conformation at 0 kilojoules per mole. So in summary, today we learned about how to draw Newman projections. First, number the carbons in your molecule and determine which carbon-carbon bond you'd like to study. Then, draw the first carbon as a dot and the second carbon as a circle. Draw the atoms around each carbon where the dashed bonds are pointing to the left, the wedged bonds are pointing to the right, and the in-plane bonds point up and down. Then we can rotate the substituents around the second carbon in the back to get different conformations. And based on stability, the staggered anti-conformation is most stable, followed by staggered gauche and the eclipsed conformations as least stable. And this stability is due to two types of strain energy, torsional strain and steric interactions, which can be broken down into their energy costs in the table shown in orange.
Organic.